All right, in these notes we're going to be talking about vertical asymptotes and holes, even though we've pretty much covered this, but there's a couple of little situations in here that are a little bit different or a little bit different side of things. So you basically already know that holes occur when something in the numerator and the denominator cancel out, when there's a common factor. And then vertical asymptotes occur when anything left in the denominator equals 0, right? So basically they both occur when this is true, but some canceling, things like that. All right, so let's take a look. So a hole occurs when the factor in the denominator cancels out with the factor in the numerator. It occurs at that number that would have been the 0 of that factor. And the vertical asymptote occurs when a factor in the denominator cannot cancel out with any of the factors in the numerator. All right, so over here on the left, holes. All right, so obviously we see this cancels, there's going to be a hole at 1. And so just to kind of look, this function now turns into this. It turns into just x plus 2. So if you were to graph this, you would see a line, the x plus 2 line, and then there would be a hole at 1. And you could also find that hole by plugging in 1. This function does not know that 1's a problem, but it is for your original. So if you plug in 1, you get 3. So it'd be a line, this line, with a hole at 1, 3. Okay, over here, if I go ahead and clean that up a little bit. So this is a little bit more to clean up, but I notice there's 2 of these x minus 1's here and 3 of them there. So these totally go away, and there will be basically 1 of these left. So I would have, on top of my function, I would have x minus 1 only, and then the bottom I would just have a 2. So really that's also a line, right? 1/2 x minus 1/2 if I were to write it, and there would be a hole at 1. So if I plugged 1 into this, my hole would be at 1 comma, and let's see, 1/2 minus 1/2. If I plug in 1, I get 0. So at 1, 0, there would be a hole. My graph would be a line again, just by chance, and there'd be a hole at 1, 0. Okay. All right. So this graph right here, also, this is how a hole is going to appear. So this is a rational function still. So these were rational functions to begin with, but they kind of turn into linear functions after that with a hole, right? I guess you'd still call them a rational function though, because anyway. All right. So this has remained a rational function looking type of picture, and here's a hole at 1, so I guess 1, 3 you could say. So that hole right there at 1, 3, so that's what's going to be what the behavior of the function would be if you were still able to go to 1, right? So from the left, your function approaches a height of 3. From the right, your function approaches a height of 3. So we get some new notation down here. All right, whenever someone puts a number right here and they have a little negative sign, that's just talking about from the left. Okay, so x is approaching 1 from the left. And put a plus sign, that's from the right. So x is approaching 1 from the right. So you're approaching 1 from the left, oh, I'm at a height of 3. 1 from the right, oh, I'm at a height of 3. That's what that's saying down here. Okay, all right, so asymptotes. So obviously, no cancellation here. There's an asymptote at x equals 1, okay? Now here, there is some cancellation, so I can cancel this out with one of these. So yes, you could say, oh, there's a hole at x equals 1, but that 1 is still a problem for you because this didn't totally go away. So it's a vertical asymptote. A vertical asymptote is stronger than a hole, right? So if it's still there after canceling, then you would say it's a vertical asymptote. Okay. All right. So again, vertical asymptote. You guys are very familiar with these, and so it's important to note on your vertical asymptotes what's happening on the right and the left now. So if I try to approach 1 from the left, my function goes down to negative infinity. If I try to approach 1 from the right, my function goes up to positive infinity. Right? Now remember, that has nothing to do with my end behavior. That still looks like 1, it looks like, but it tells you as you approach 1 from the left, you're going down. As you approach 1 from the right, you're going up to positive infinity. So you're going to get that new notation with the left and the right. Okay, now that's a good point to talk about the normal behavior of rational functions. So you don't have to write this down or maybe jot it down somewhere, but if you have like 1 over x, your basic rational function, so your asymptote, your vertical asymptote's at 0, and actually your horizontal asymptote's at 0 too. So you guys know just real quick that looks like this. This is like kind of normal. The right side's up, the left side's down, you know, go into your horizontal asymptote. If you were to put a negative, all right, then obviously these would switch places. This one would be up here, this one would be down there. Okay, so what I'm doing for you is if you have a vertical asymptote and there's a positive up here, then you know that usually what's going to happen is to the right of it goes up, to the left of it goes down. If there's a negative, it flip-flops. Now, one other situation is if you have a square. If your asymptote is squared, what ends up happening is both sides are now going up, right? Because that number, whatever numbers are around it are being squared and so creating positive. If that was a negative, I had a negative with it, obviously it'd be the same graph, but it would just be like flipped over, right? Okay, so it's just like generic behavior of rational functions in general. Okay, let's get to the second page. All right, so we're going to go ahead and give the coordinates of any holes in these problems, or also any vertical asymptotes. We're going to write the equation of them. All right, oops, sorry, up here. All right, so I do see a cancellation. So that means that this problem now becomes x minus 2 over x minus 5. You don't really need those parentheses anymore. So let's see, I am going to have a hole here, and it's going to be at -3 something. So the way to get the answer for the hole is to plug -3 into the remaining part. So -3 minus 2 is -5. -3 minus 5 is -8. So -5 over -8, that would be 5/8. Right, and then I still do have a vertical asymptote in this problem of x equals 5. Okay, all right, over here, let's see. All right, so this cancels. So I would say to myself, I have a hole at 2, x equals 2. I'm going to start a point for a hole. And sometimes people might want the point, or they just might want you to say at x equals 2, there's a hole. All right, but also what happens here is that x plus 1 cancels. But when x plus 1 cancels, there's still more of it down in the denominator. So that means that -1 is going to be an asymptote. All right, because this problem turns into x plus 1. And on the top, what do I have? An x minus 2. All right, so it was going to be a hole at -1. I would have put another one here. And you can have 2 holes, but it's stronger now because it's still an asymptote. So my vertical asymptote is at x equals -1. If I plug 2 into here, I would get 0 over 3, so 0. All right, over here, let's see. I don't see any cancellation because there's nothing on top really, but I do need to factor x would come out, and I have x squared plus 4 left. All right, so no holes, but I have a vertical asymptote at x equals 0. All right, so this also, you could like factor that, but it's going to be imaginary numbers, right? And so obviously we're not going to see any imaginary asymptotes. So if you're factoring or you're solving here would produce imaginary solutions, and you don't have to worry about it. Okay, all right, so no holes there. All right, we are going to write right and left hand, or left and right hand limit statements as you approach 2. So all these problems have something going on at x equals 2. So that's what they were made for that. All right, so right here, I have to decide what's happening at 2 here. So there's no cancellation, so that means I have a vertical asymptote at x equals 2, right? So a vertical asymptote means to the left and to the right, I'm going to go to infinity or negative infinity. So my limit, excuse me, as x goes to 2 from the left, put a little negative sign, of this function is, and down here my limit as x goes to 2 from the right of f of x is. Now, this problem is pretty simple, like there's no, I don't know, let's see, like I guess it's going to be a slant asymptote because the x squared on top and the x on bottom, but there's no kind of other craziness, so I can pretty much trust there's no negative out here, these x minus 1, it's not 1 minus x, creating a negative. I'm pretty confident that around 2, like it's going to basically act like this, right? Right side and left side goes down. Oopsie. So we're going to plug in some numbers just to be certain, but we're going to plug in some numbers around 2. So I want to test numbers like right around 2, right? So if I test f of, let's say 3, because right around 2 I expect some behavior, all right? And I would say to the other side of 2 would be 1, but this guy right here, 1 minus 1, is going to make me a 0, and that doesn't really tell me anything. So I'm going to do like 1.5. And I'm really just kind of interested in like what's going on here. All right, so if I put in 3, if I put in 3 here, I got 3 minus 1, so that's a 2. 3 plus 3 is 6, and 3 minus 2 is 1. So I'm just getting a nice positive, I get a 12, right? But it's positive. But 1.5, let's see. 1.5 minus 1 is positive. 1.5 plus 3 is positive. 1.5 minus 2 is negative. So you see I'm going to get a negative. All right, so that doesn't always work, but the closer you are to the asymptote, the more it's going to act like you think it should, but we'll also graph it just to make sure. Okay, so this guy from the left is going to negative infinity because it's following this idea, and on the right it's going to positive infinity. All right, so just to clarify or confirm, we'll go to our calculator. Now I have a bunch of problems entered in here from our notes, and hopefully you realize that on this equal sign, if it's blackened in, if you press enter, that's going to graph that. So that's this problem that we're doing right now. And I have all other ones turned off. Yep. All right, so let me graph that. All right, so to the left it is going down. I can't really see to the right, so let me change my window, and I just want to see a little bit higher. Let's see if that'll do it. Yep, there it is. Okay, so over here cancels. So this problem becomes x plus 4 and x minus 3. So I do not have infinity behavior here. I do not go up to infinity or negative infinity because I actually have a hole here. All right, so the hole is going to be at 2. And if I plug 2 into this, I get 6 over negative 1. So I get negative 6. Okay, so what's going to happen, it's going to be like this picture. As I approach 1, I'm coming to an actual value. I'm coming to a height. Remember, my limit is my intended height of my function, right? Like the y value, right? Okay, so here we go. The limit as x goes to 2 from the left of my g of x is going to be that negative 6. And my limit as x goes to 2 from the right of g of x is going to be negative 6 also. All right, so a way that you can check this on your calculator, if you can use your calculator, is this. All right, so let me go and turn that one off, and go down, turn this one on. That's the one. All right, oh, let me get my regular picture back. So also, if you want to stop your graph, you can press the on button, and that pauses your graph, and then you can like do something, press other buttons. Otherwise, you have to wait up here till it finishes graphing. This little like sneaky little thing is going to be moving around. All right. So we're trying to check about negative 6, right? I'm sorry, at 2 we're trying to check. So what I can do is press trace. Let me type in a number around 2, like 1, right? All right, so there it is. So you see if I type in 2 and press enter when I'm on trace, it gives me nothing. There's nothing there. That's the rest of the graph. So if I move immediately to the right of that, you see how it's negative 7. If I go to the left of 2, at 1.9, it's negative 5. So like what's right between negative 5 and negative 7? Hey, guess what? Negative 6, right? Okay, so anyway, that's how you can kind of test to make sure you're kind of getting it right, because it won't tell you the answer at the hole because it's a hole. All right, over here, let's see, I put a little negative sign there. I think it's on your paper already. Let's see what's happening here. X minus 2 is going to cancel, and it's still there. So it's not a hole, it's a vertical asymptote. So there's vertical asymptote at x equals 2. So that means I'm going to go off to infinity or negative infinity. All right, so my limit as x goes to the 2 from the left, sorry, of h of x. And my limit as x goes to 2 from the right of h of x. Okay, so what's going to happen here is you have your normal behavior here, but what's happening around, you have a negative around in there. So your graph is being kind of like turned over. All right. So when you approach your vertical asymptote, what's going to happen is, and you got two of them here, but what's going to happen is it's going to go up on the left and down on the right is what should happen. All right. We'll graph to confirm, but you could also try some numbers around too, like we did back here. So I'm going to do that on my calculator just to make it faster. So let's see, go back to y equals, let me turn this guy off. This is my third one. Yep. All right, so I'm going to try by plugging in some numbers because it's kind of annoying to plug numbers into that, right? All right, so let's see. So let me do alpha trace, oh, let me check, y3. All right, so alpha trace, let me choose y3, and let me plug in a number like right before 2, like, let's even plug in like 1.9, like really close to 2 on one side. All right, because, you know, 1.5 I was just doing earlier because it was in my head. All right, so that's a positive number. So like we said, going up. And let's type in a number like right after 2. So if you press second enter, I can just change this to like 2.1. It's right after 2. Oh, crap. No, not that. On. I just want to enter. There you go. So negative. All right. So it's very positive right before 2, and it's very negative right after 2. Okay. So positive infinity, negative infinity. And you can look at the graph and you can see that happening there. All right. Almost done here. So I need to create an equation that has these properties. So let me just start f(x). And so first I notice that it looks like they want me to have a hole at 3. So I need x minus 3, something to cancel out. Okay. And then it looks like I want an asymptote at 1. So I need an x minus 1 down here. All right. So it's normal behavior, down on the left, up on the right. So I'm not going to put a negative sign. But when I cancel this 3 out and I plug 3 in, I need the answer to be 5, right? That needs to be the whole of the graph. So when I cancel this out right now, I don't get that. And I remember I'm plugging in 3, so I'm getting a 2 here. All right. So I need the answer to be 5. So I think I can just put like a 10 up here, right? So if I have 10, oh, I'm sorry. I'm very silly. All right. Not a 10. All right. Sorry about that. When I plug in a 3, all right, 3 minus 1 is 2. Oh, yeah, if I put a 10, right? Because 10 over 2 will be 5. Okay, sorry, I like unthought myself. All right, so there's my problem. Okay, I created a problem that this would happen for. And you could check it on the graph if you want, right? And this is going to vary. Like in my example, I instead of putting that 10, I put 4x minus 2. Like when I was working this out myself, I don't know why I just didn't think of 10. Because when I put 3 into this, I got 12 minus 2, which was 10, and 10 over 2 is 5, all right? I don't know why I was being all complicated, but, you know, that could be there as well, okay? All right, so over here, so it looks like my f of x needs to be, let's see, a whole at -2, so I'm going to have x plus 2. All right, and I'm going up to positive infinity on both sides, so that means I want this asymptote at x plus 1 to be squared. Okay. All right, and so let's see, I want the whole to be at -2 and 4. So let's see what we could do. So if that cancels out, -2 plus 1 would be -1, and -1 squared would be 1. So this isn't going to do anything to me, so I'm just going to put a 4 up here, because 4 over 1 would be 4. And there we go. All right, this part down here will be a little bit easier. All right, we're just going to draw a picture. We want there to be a hole at 1, so I'm going to put a 1 right here. I'm going to know there's going to be a hole there. I want, as you approach 4 from the left, I want you to go up forever. So 2, 3, 4, so that means there's a vertical asymptote here. So I'm going to draw this, make a hole, and this goes up forever. All right, as x approaches 4 from the right, it has to go down. So I'm just going to draw this coming down. Fine. And this could be like anywhere, like along, it could be up some, down some. I don't have to have a vertical, horizontal asymptote of 0. All right, over here, oh, 2 holes, -2 and 1, 2, 3. And when you approach -1 from the left, we go down, and from the right, we go down. So -1 must be a vertical asymptote. And I think I'm just going to do this. I'm going to make it down here so I can see it. So here, hole, and then continue down. And then over here, hole, and then continue down. Okay, so that's about as easy as I can make it. I don't know, there are many pictures that could do this. All right, that's it. Go do your Desmos, and you got the paper for this for homework. And I'll see you next time. Bye-bye.